In the early 1950s, hydraulic engineer Simcha Blas was working in the Jordan Valley when he noticed something strange. One tree had grown twice as large as the others. No one had deliberately watered it. Near its roots, a thin pipe was quietly leaking water. What he saw defied common sense. A tree receiving almost no water had grown larger than those being watered. For 10 years, Blas would try to figure out why. The answer he found would transform agriculture across an entire country and eventually spread to 110 countries around the world. Israel is a country where more than half the territory is desert, and the only freshwater river is the modest Jordan. Yet today, Israel produces roughly 95% of its own food. In 1948, when the state came into existence, that would have sounded like madness. Even a century ago, British geologists described the Negev as practically dead land, arid and semi-arid climate, only 50 to 150 millimeters of rainfall per year, saline soils. Almost nothing grew here without constant human intervention, but the problem was not just the quantity of water, it was how water was being used. Conventional flood or sprinkler irrigation throws water onto the surface, where much of it is lost to evaporation, wind, seepage below the roots, and runoff. No matter how much water was pumped into the system, only a fraction reached the roots. Forests were planted, they grew, the canopy closed, and it seemed the problem was solved. Then a drought would come a few years later and everything started from zero. No budget can sustain that indefinitely. To change anything in this equation required someone who understood the physics and was stubborn enough to search for the answer across decades. Simcha Blass was born in Warsaw into an Orthodox Jewish family. As a young man, he decided that engineering was the only way to build something real in Palestine, not with words, but with pipes, concrete, and water. Between 1930 and 1948, he became the most prominent water engineer in the Jewish community of Palestine, designing the first modern aqueduct in the Jordan Valley and co-founding the water company Mekorot in 1937 alongside Levi Eshkol and Pinhas Sapir. But the most important episode came in October 1946, 2 years before independence was declared, when nothing had yet been decided. The British UN Commission was leaning toward excluding the Negev from the future Jewish border. The argument was simple and, on the surface, unanswerable. Who needs a desert? Blass understood that diplomatic negotiations move slowly and facts on the ground work faster than words. He purchased pipes that Britain had used to fight fires during the London Blitz. And on the night of October 6, 1946, dozens of people went out into the desert. Among them were not only engineers, there were teachers, doctors, former soldiers, people who had not held a shovel the day before. Each of them knew, if the commission cut off the Negev, what would be lost was not just a patch of sand, but the space without which the future state would suffocate. And each understood that this night was the only window. The British would make their decision by morning, and by morning there had to be settlements with running water standing on this ground. They worked through the night, trenches, pipeline, connections, all of it in darkness. When the sun rose, the commission saw not an empty desert, but 11 new kibbutzim with functioning water supplies. A fact that could no longer be filed away in a diplomatic folder. The Negev remained within the borders of the future Jewish state. The pipeline had done its work, but for the people who stayed to live on that sand, everything was only beginning. One of those 11 kibbutzim was Hatzarim, 8 kilometers west of Beersheba. Its first years were barely survivable. The soil proved so saline that most crops simply died. Members of the kibbutz seriously discussed leaving and moving somewhere the land offered at least a chance. The government persuaded them to stay, insisting that every settlement in the Negev mattered to the strategic integrity of the country. In 1959 came the moment of final decision. At a general meeting of the kibbutz, the question was put plainly, do we go or do we stay? As participants later recalled, nobody gave speeches. There was a brief discussion, a show of hands, and silence. People walked outside and returned to what they did every day, trying to grow something on land that refused to allow it. That same year, Blass appeared at Hatzarim. He laid thin plastic tubing along the ground with small devices, drippers, spaced at regular intervals. Each dripper delivered water not onto the soil surface, but slowly, drop by drop, directly to where the roots began. No sprinklers, no channels, no open water on the surface. just a tube running along a row of trees, barely visibly wet at a single point. This was the first experimental drip irrigation system in the Negev. The tree near the leaking pipe had given Blas no peace. Before the system ever appeared in the field, he had spent years in the laboratory dismantling the mistakes of every previous approach, trying to understand why slow water delivered at the root had produced such a result. The idea of drip irrigation had existed long before him. Various engineers had tried running water through micro openings. The logic seemed flawless. A small hole, a small drop, fewer losses. But in real conditions, this logic would break down within a few weeks. A grain of sand, a mineral deposit, any organic particle, and the micro opening clogged. When such points number in the thousands per hectare, maintaining them becomes impossible. The system would disintegrate faster than it could show any result, and each attempt ended the same way: blocked tubes and disappointment. Blas took a different approach. Instead of making the opening smaller, he made the channel longer. Inside the plastic dripper, water traveled through a wider but longer labyrinth, where friction gradually slowed the flow. The wider channel did not clog with particles. A grain of sand that would instantly block a micro opening passed freely through the labyrinth channel and was carried out with the water. A drop appeared at the exit slowly and evenly, not because the opening was small, but because the path was long. This turned out to be the key to the entire system. Not a smaller opening, a longer path. The solution looked so simple that the initial reaction from colleagues was skeptical. Engineers who had spent years working with micro openings could not believe the answer lay not in precision machining, but in the geometry of the channel. But the dripper design itself solved only half the problem. Equally important was the principle of delivering water to the plant. When water falls from above or spreads across the soil surface, most of it never reaches the root zone. It evaporates, runs off, or seeps deeper than the roots extend. The plant receives a brief pulse of moisture, then dries out again until the next watering. Drip irrigation changes this dynamic entirely. Water is delivered directly into the root zone, in small doses but continuously. The plant receives exactly as much as it can absorb at any given moment, without waterlogging and without drying out between cycles. Water use efficiency in drip irrigation reaches 95 to 100%. By comparison, sprinkler systems achieve 80 to 85%, and flood or furrow irrigation only 60 to 70%. The first experimental system, installed in 1959, showed that trees produced nearly twice the yield with significantly less water consumption. Not 10 or 15% better, twice. For a kibbutz that had spent years barely surviving on exhausted land, these numbers changed everything. As Hatzarim's members later recalled, after the first harvest, the question no longer existed. But between a working prototype in the field and an industrial product that could be sold to thousands of farmers lay a gap that Blas could not cross alone. The first obstacle was material. Plastic in the form needed for manufacturing drippers only became available after World War II. It was precisely the arrival of modern polymers in the late 1950s that gave Blas the ability to take the next step. He had left government service back in 1956, reopened his private engineering firm, and together with his son Yeshayahu began turning the laboratory idea into a product suitable for mass production. The second obstacle was human. Blas was an engineer. He understood physics, materials, and construction. He was not an entrepreneur, and he needed a partner with manufacturing capacity. Someone who understood agriculture from the inside and could organize cereal production. In 1965, Blas approached Ari Bahir, who was responsible for industrial development of kibbutzim, and asked him to find such a partner. From several options, Blas chose Kibbutz Hatzarim, 20 years on land where almost nothing had grown. These people knew the problem not from textbooks and had already decided not to retreat. For them, it was a matter of survival, not a business plan. On August 10, 1965, Blas, his son Yeshayahu, and representatives of Kibbutz Hatzarim signed a contract establishing Netafim Irrigation Company. The kibbutz received 80%, the Blas family 20%. The first factory opened in 1966, and the first sales to Israeli farmers began in 1967. But even with a working product in a factory, selling turned out to be no easier than inventing. Farmers had known one method for decades: flood irrigation. For them, water was supposed to flow across a field or spray from sprinklers, and a thin plastic tube with some sort of drippers looked like an unnecessarily complicated and unjustifiably expensive way to do what could be done with a bucket or a channel. To overcome this skepticism, Netafim had to build demonstration plots and show the difference in yield before and after on the same fields. One of the first demonstrations that Netafim veterans used to describe had a simple structure: 2 adjacent plots with the same crop, one with a sprinkler, one with a drip system. After a season, the difference was visible to the naked eye, without any measurements. A farmer who had initially refused to let Netafim onto his land placed an order for his entire holding the following week. Word spread among neighbors, and that turned out to be more effective than any advertising. Over the following decades, Israel transformed drip irrigation from experiment to national standard. Where only barley had grown before, tomatoes appeared, then peppers, date palms, citrus. The Arava, a strip of land between the Dead Sea and Eilat where annual rainfall does not exceed 30 millimeters, became one of the largest exporters of fresh vegetables to Europe. In winter, when European fields stand empty, Israeli farms in the desert dispatch tons of tomatoes and peppers. By the end of the 1970s, drip irrigation covered the majority of Israeli agriculture. The country whose founders had built on canned goods and imported grain began exporting fresh produce and agricultural technology. The Negev itself had become a laboratory. The data began accumulating within a few seasons, and with each year the picture grew more convincing. To understand the scale of what happened, you need to look at Israel in 1948 and Israel today as 2 different countries. In 1948, the young state imported most of its food and lived on ration cards. The first kibbutzim grew whatever could survive: barley, millet, and a few varieties of vegetables. The Negev stood empty. Farmers in the north flooded their fields with water from the Sea of Galilee and lost more than half before it reached the roots. Today, those 95% are reality, not fantasy. Agricultural output since 1948 has grown roughly 16-fold, while water consumption per unit of yield has fallen dramatically. The country does not merely feed itself, it has become one of the largest exporters of fresh vegetables, fruit, and flowers to Europe. Drip irrigation changed not only crop yields, it changed the entire economics of water in the country. When every drop goes directly to the root, it becomes possible to use water previously considered unsuitable: treated wastewater, slightly saline groundwater, and desalinated seawater. Israel has built an entire system on this. Today, the country recycles and returns to fields around 90% of its wastewater. For comparison, Spain, second in the world on this indicator, recycles less than 20%. 5 desalination plants on the Mediterranean coast supply more than half the country's drinking water. Israel has effectively stopped depending on whether or not it rains in any given year. But perhaps most important is what happened to the Negev itself. The land that British geologists declared dead in the 1930s has become an agricultural region with hundreds of farms, research centers, and a university in Beersheba that is today one of the world leaders in arid land agriculture. Technologies developed in the Negev now operate on fields across dozens of countries. The country that began with imported grain and ration cards became an exporter not just of food, but of knowledge about how to grow food where it seems impossible. Netafim moved beyond Israel and implemented drip irrigation systems in more than 110 countries. The company captured 30% of the global micro-irrigation market, built 17 factories, and grew to more than 4,000 employees. On a Peruvian sugarcane farm, a 60% reduction in water use was documented compared to the previous irrigation method. In the Indian state of Jharkhand, farmers who installed drip systems on credit repaid their loans within 5 months, thanks to a sharp increase in net income from the same plots. And there is one more detail, with a considerably longer history than anyone might expect. The principle that Blas discovered while watching a leaking pipe is described in the Chinese agronomic treatise Fan Shengji Shu, written in the 1st century BCE. 21 centuries ago, Chinese farmers buried unglazed clay pots filled with water in the soil, and it seeped slowly through the porous walls directly to the roots. The same logic, the same principle. But behind this success lurks an uncomfortable question. After 60 years of existence, drip irrigation still covers only a small fraction of global agriculture. 3/4 of irrigated land in the world is still watered the old way, by flooding, furrows, and canals. The technology works better than any alternative, but its upfront cost remains a barrier precisely for those who need it most acutely. According to UN estimates, 500 million smallholder farmers provide more than 80% of the food in developing countries. For a farmer in Rajasthan or Ethiopia, working half a hectare by hand and waiting for the monsoon, even the cheapest drip system represents an entire year's income. Subsidies and microcredit exist, but rarely reach the most remote villages. Netafim itself has traveled a long road from a kibbutz in the desert. The company born in a community that decided not to give up is today 80% owned by the Mexican conglomerate Orbia. Kibbutz Hatzerim retained 20% and became one of the wealthiest kibbutzim in Israel. But the question of whether this technology will reach the places where water disappears first remains open. Simcha Blas died on July 18, 1982. By that point, Netafim was already selling systems far beyond Israel, and the technology he had launched from a single leaking pipe was operating on fields in dozens of countries. But he could not have anticipated the scale of the challenge his invention would face 4 decades after his death. Agriculture still consumes roughly 70% of all the planet's freshwater resources. The climate is changing, and droughts are becoming not just more frequent, they are becoming longer and deeper, striking regions that 10 years ago were considered adequately wet. By projections, humanity will need 70% more food by 2050 to feed a population that keeps growing. Meanwhile, arable land shrinks each year, consumed by salinization, erosion, and urban sprawl. Drip irrigation answers part of this equation, but only part. Netafim acknowledges this and has long moved beyond the simple tube with a dripper. The company develops digital irrigation management platforms, sensors that track soil moisture in real time, integration with satellite data on crop condition. The goal is for the farmer to receive not a tube requiring manual calibration, but a system that determines on its own when, how much, and where to deliver water. Efforts to reduce system costs are also advancing. Several companies, including Netafim, are developing gravity-fed kits that work without electricity or a pump. Water flows from a raised tank under its own weight. India subsidizes up to 90% of the cost of drip systems for smallholder farmers. Startups in East Africa are testing subscription models where the farmer pays not for equipment, but for a season of use. But the scale of these initiatives does not yet match the scale of the problem, and the driest lands, where a farmer depends on every raindrop, remain largely out of reach. The leaking pipe in the Jordan Valley answered the question of physics. The question of economics and access remains open.